Hello, this is video number 5 in the series Mastering the INCOSE System Engineering Handbook in preparation for the INCOSE System Engineering Professional Exam. Video number 5 covers the architecture definition process, section 4.4 of the INCOSE System Engineering Handbook. My name is Lance Sherry, and I will be your tour guide for this video. So as we said in the introductory videos, the INCOSE System Engineering Handbook defines the system lifecycle processes and activities that provides a structured approach to developing systems that are themselves inherently complex and then are developed and deployed in very complex life cycles. Within the System Engineering Handbook, there are 59 system engineering lifecycle processes and activities, and those are organized into 7 categories. This video deals with system requirements definition process in section 4, known as the technical processes. The architecture definition process, shown in the bold, is closely related to the design definition process. So architecture tends to be conceptual while design gets into the details of the technology. And as a consequence, these two processes kind of go hand in hand. The SE Handbook separates them out, and we're going to brief them in separate videos. So the learning objectives for this video is what is an architecture? What is the purpose of the architecture definition process? And then the outputs, inputs, and process activities. 6 provides a little bit of information on the characteristics of a well-defined architecture. 7 gets into the functional allocation process, and then number 8 is the output of this process is the system element requirement specification. So to kind of put things in a broader context, this diagram figure 4.1 from the System Engineering Handbook defines the documents that are generated as the business requirement specification, followed by the stakeholder requirement specification, followed by the system requirement specification, and then on the 4th tier we have the system element requirements specification, which captures both the architecture and the design. So just to take a step back and provide a definition for system architecture. The system architecture is the fundamental organization of a system that is embodied in its components. It defines the relationship between the components and the relationship between the environment and the system components. So we're taking an English language, the system shell requirements view of the system, and we're converting that into a functional or an object-oriented or a behavioral view of the system that's based on the components and the interaction between the components. So as we discussed previously, from our Greek philosopher, there are several ways of describing a system. And for the architecture purpose, there's the behavior, the data flow, and the object-oriented. So the behavior has a focus more on what the system is going to do, how it responds from inputs to outputs. The data flow shows the flow of information and data through the system. And then the object orientation shows the components and the relationship between the components. So an architecture can have multiple views of the same system. So one other term to introduce is this idea of functional allocation, and that's the idea of knowing how to break up the components in the most sensible manner. And we'll discuss that a little bit further, a little bit more as we go on. So related to the definition of architecture is the distinction between system architecture and system design. And as we said earlier, these two things are closely related. The architecture tends to be more abstract. It tends to be a conceptualization of the design of the system. It's very much focused on the mission and the OpsCon and provides a very high-level structure and elements. The design is completely technology agnostic or design agnostic, and what we mean by that is that the architecture does not have any design decisions that are based on implementation on technology. So it's a kind of a utopian view of how one would organize a system if you could wave a magic wand and have any kind of technology available for implementing the system. So that's the architecture. Now the design is a lot more focused on exactly how things will be implemented in terms of the alternate technologies. So the design tends to be more technology oriented. It takes into account the physical structure, environmental and operational properties, and it's very specifically focused on the compatibility with technologies and the feasibility of construction and integration. So system architecture is abstract and design technology agnostic, while the system design is very much focused on how it will be implemented and the technologies that will be used. So the system engineering, the system architecture definition process, as defined in the INCOSE SE Handbook, has the purpose to generate the system architecture alternatives, to frame stakeholder concerns and meet system requirements, and to express these in a consistent set of views. So the result of this process is the system element requirement specification. So in plain language, we're going to take your requirements, the system shall fill in the blank, and come up with a set of interrelated components that generate the required system behavior that will subsequently lead to a design that will lead to implementation. So the outputs, inputs, and activities for this diagram, well, you can see the output is a system element requirement specification in a behavior, functional, or object-oriented view. There's a sequence of activities to generate that that are related to architectural viewpoints, models, and then trade-off between alternate architectures. And then the inputs are everything that came before it in the engineering development process related to the requirements. So the system element requirement specification will typically use SysML, LML diagrams, figures, and tables. So because we're looking at architecture, it tends less to be written requirements and more diagrams. So the architecture definition process converts requirements into a set of interrelated components that generate the required behavior. And to do that, there have been developed a set of frameworks that assist the engineer in developing the architecture. The frameworks themselves are kind of a common approach for presenting, describing, and comparing enterprise architectures. And they're designed to allow people from different organizations or multinational boundaries, in the case of defense systems, to view the same system. The frameworks promote use of a common terminology and assumptions. So they encourage a language and definition of terms that makes sense to all of the potential users of the product and the designers to come up with an architecture that can be understood and used by everybody. And they're particularly suited to large systems with complex integration and interoperability challenges. So this is a very interesting topic in itself with frameworks, and this video can't do justice to the topic. But some of the more common examples from the defense systems world is the DODAF. The Open Group Architecture Framework is more of an enterprise view. The Federal Enterprise Framework is obviously more federal systems, and then there's the 4+1 architectural view model, as well as many other frameworks. So each of these frameworks is equally good and kind of focused on its specific domain. So one of the first things one does in developing an architecture is establish the system boundary. So we want to draw a black box, an input-output, put our system in the middle, and establish what comes in and what goes out. And that identifies the system boundary. Of course, this is a very non-trivial activity and really starts the process of scoping down from a concept to an implementation. The next thing is to allocate functions or objects in the architecture. So the very highest level and most obvious allocation is to separate out the human operator from the automation. What tasks, what functions will the human operator perform, and what tasks and functions will the automation perform? At the end of the day, we're always building systems that are human-machine systems. We're not just focused on the machine or the automation part. We've got to take into account the human operator and their roles. So the very first thing that's typically done in architecture is to separate out the human functions, functions allocated to humans, from the functions that are allocated to the automation. And then within the automation, there are going to be functions that are performed by the automation, and those need to be allocated. The process for doing this is a really fascinating process, and it's got one of the ways that it's known is a functional allocation, and that is a top-down process for translating system-level requirements into a detailed functional representation. And again, it's a fascinating topic and more than we can cover in this short video. So once one has an architecture, the question is what constitutes a good architecture? And there's several attributes. The two most important are coupling and cohesion. So coupling is the interdependence between components. And when you have components that are too interdependent, it's called tight coupling. And you can imagine that if you have a component that fails, that will cause all the downstream components to fail. Or if you have a component that generates an inaccurate information, inaccurate data, that all of the systems that are attached connected to it, coupled to it, would pick up that information as well. So tight coupling is something that should be avoided. The second thing is cohesion, and that is the how closely related functions are within a single group of components. So you'd want to have functions that are closely related, connected to each other, and you'd want to avoid a situation where you have a collection of components that are not really related to each other. So the whole idea is to avoid low cohesion. So at the end of the day, you will come up with alternate architectures. There's probably not one architecture that's going to be superior than all the others. And so it's not unusual to have a set of candidate or alternate architectures. And the question is how do you pick the best one? Well, one approach is to use a multi-attribute utility theory, where you calculate the utility for each individual architecture and then trade that off with an estimate of life cycle costs. So in this example on the left-hand side, we've got architectures 1, 2, 3, and 4. Those are alternate candidate architectures. Each one of those architectures is scored based on its utility and then plotted on the chart as utility versus life cycle cost. So architecture alternatives 1, 2, and 3 have the highest utility with increasing life cycle costs. Architecture 2 has better utility than 1 but costs more. And architecture 3 is better utility than 2 but costs even more. So you can kind of see how architecture designs 1, 2, and 3 create a Pareto frontier. The utilities are estimated or calculated based on a value hierarchy or a set of a weighted sum of attributes, and those attributes are scored and then multiplied by the weights and then summed together to generate the overall utility for the individual architectures. So with that, we come to the end of this video, and here's an opportunity to test yourself on what you've learned. What group of processes and activities does the architecture definition process fall under? What document is generated by the architecture definition process? Number 3 says give a definition of system architecture. 4 is list 3 types of information that are used as input to the process. And then 5 asks you to identify 2 characteristics of a good system architecture. 6 is to provide a definition of functional allocation. And 7 is to give an example of functional allocation. 8, how are design alternatives evaluated? And then number 9 is what is the highest level architecture diagram, and what information does that convey? So hit the pause button right here, answer the questions, and when you're done you can go to the next slide and check your answers. So thank you for taking the time to go through the video. If you could give us a thumbs up on the YouTube. And the next video is video number 6, and that is the design definition process.